Welcome to Sleepy Science Odyssey. Tonight, the Andromeda Galaxy, our nearest large galactic neighbor, a vast spiral of stars, gas, and dust stretching across 220,000 light-years, will move slowly through this cosmic island, exploring its structure, its history, and its future collision with our own Milky Way. We'll visit its spiral arms, its supermassive black holes, its trillion stars, and the hundreds of smaller galaxies that orbit it. We'll trace its past through ancient collisions and look ahead to the merger that will reshape our corner of the universe billions of years from now. If you're new here, this channel is for people who need something to think about before they can stop thinking. Real science, no hype, just quiet facts in the dark. Let's begin. Andromeda is also known as Messier 31 or M31. The designation comes from the catalogue compiled by French astronomer Charles Messier in the 18th century. Messier was a comet hunter, and he grew frustrated by fuzzy objects in the sky that resembled comets but didn't move. They were permanent features, not wandering visitors to the solar system. To help himself and other astronomers avoid confusion, he compiled a list of these objects. His catalogue, published in various editions between 1774 and 1781, eventually included 110 objects. Ironically, though Messier intended his catalogue as a list of things to avoid, it became one of the most famous astronomical catalogues, containing some of the most beautiful and interesting objects in the night sky: galaxies, nebulae, star clusters, and supernova remnants. M31, the Andromeda Galaxy, was the 31st object in his catalogue. Today, astronomers still use Messier numbers alongside other designations. The Andromeda Galaxy is also catalogued as NGC 224 in the New General Catalogue, compiled in the 1880s by John Dreyer. But M31 remains the most common designation among amateur astronomers and in popular usage. The galaxy itself has been known since ancient times. It's visible to the naked eye from dark locations as a faint, fuzzy patch in the constellation Andromeda. Ancient astronomers observed it and recorded it in various texts, though they had no idea what it was. The Persian astronomer Abd al-Rahman al-Sufi described it in 964 AD as a small cloud in his Book of Fixed Stars. It wasn't until the 20th century that astronomers realized M31 was not a nebula within the Milky Way, but a separate galaxy millions of light-years away. Andromeda is about 2.5 million light-years from Earth. This distance was one of the most important measurements in the history of astronomy because it revealed that the universe extends far beyond the Milky Way. In the early 20th century, astronomers debated whether the spiral nebulae observed through telescopes were clouds of gas within our galaxy or separate island universes far beyond. The debate, sometimes called the Great Debate, came to a head in 1920 when astronomers Harlow Shapley and Heber Curtis presented opposing views. Shapley argued that spiral nebulae were part of the Milky Way, while Curtis argued they were separate galaxies. The question was resolved in the 1920s by Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory in California. Hubble identified Cepheid variable stars in Andromeda, stars whose brightness varies predictably with a period related to their intrinsic luminosity. By measuring the period of these stars, Hubble could determine their true brightness. Comparing their true brightness to their apparent brightness as seen from Earth allowed him to calculate their distance using the inverse square law. In 1924, Hubble announced that Andromeda was about 900,000 light-years away, far beyond the boundaries of the Milky Way. His distance estimate was later revised upward. We now know Andromeda is about 2.5 million light-years away, but the fundamental conclusion remained: Andromeda is a separate galaxy. This discovery transformed our understanding of the universe. The Milky Way was no longer the entirety of creation, but one galaxy among countless others, scattered through an incomprehensibly vast cosmos. The observable universe, we now know, contains hundreds of billions of galaxies, each home to billions or trillions of stars. Andromeda is approaching the Milky Way at about 110 kilometers per second. This is unusual because most galaxies are receding from us due to the expansion of the universe, discovered by Edwin Hubble in 1929. Hubble found that distant galaxies are moving away from us, with their recession velocities proportional to their distances. The farther away a galaxy is, the faster it's receding. This relationship, now called Hubble's law, implies the universe is expanding, with space itself stretching and carrying galaxies apart. However, this expansion only dominates at large scales, tens or hundreds of millions of light-years. At smaller scales, gravity can overcome expansion, binding galaxies into groups and clusters where they orbit each other or even collide. The Milky Way and Andromeda are members of the local group, a collection of about 80 galaxies bound together by gravity. Within the local group, galaxies move according to their mutual gravitational interactions, not the expansion of space. Andromeda and the Milky Way are the two dominant members of the local group, much more massive than the others, and their gravity has been pulling them together for billions of years. Observations of Andromeda's motion show it's approaching us at about 110 kilometers per second, or about 400,000 kilometers per hour. This might sound fast, but given the enormous distance of 2.5 million light-years, it will take about 4 billion years for the galaxies to collide. The approach velocity is measured using the Doppler effect. Light from Andromeda is blue-shifted to shorter wavelengths, indicating the galaxy is moving toward us. Most galaxies show redshifts, indicating they're moving away, so Andromeda's blue shift is notable. It's one of the few large galaxies approaching us, along with a few others in the local group. Andromeda is the largest galaxy in the local group. It contains about 1 trillion stars, roughly double the Milky Way's 200 to 400 billion. This makes Andromeda the dominant galaxy in our local neighborhood, with a mass perhaps 50% to 100% greater than the Milky Way's, depending on how dark matter is distributed. For decades, astronomers thought Andromeda was significantly more massive, perhaps twice or 3 times the Milky Way's mass. More recent measurements, particularly of the Milky Way's mass including its dark matter halo, have revised this view. The two galaxies may be more comparable in mass than previously thought, with Andromeda still somewhat larger, but not overwhelmingly so. The exact masses are still uncertain because most of each galaxy's mass is dark matter, which doesn't emit light and must be inferred from gravitational effects. Estimates of Andromeda's total mass range from about 800 billion to 1.5 trillion solar masses, while the Milky Way's total mass is estimated at about 800 billion to 1.5 trillion solar masses as well. The ranges overlap, indicating the uncertainty. Regardless of the exact numbers, Andromeda is clearly one of the most massive galaxies in the local group, along with the Milky Way. The third largest, the Triangulum Galaxy, M33, is much smaller, with only about 40 to 60 billion stars and perhaps 10% the mass of Andromeda. The rest of the local group consists of dwarf galaxies, small collections of stars ranging from a few million to a few billion, many of them satellites orbiting either the Milky Way or Andromeda. Andromeda is about 220,000 light-years across. This diameter refers to the visible disk, where most of the stars reside. It makes Andromeda significantly larger than the Milky Way, which is about 100,000 to 120,000 light-years across, depending on exactly where you define the edge. Andromeda's greater size is one reason it contains more stars. It has more room. The galaxy's disk is not perfectly circular but slightly elliptical, and it's also warped, with regions tilted at different angles. This warp is visible in radio observations of neutral hydrogen gas extending beyond the stellar disk. The cause of the warp is likely gravitational interactions with Andromeda's satellite galaxies, which pull on the disk and distort its shape. Like the Milky Way, Andromeda has a thin disk where active star formation occurs and a thicker disk or halo containing older stars. The thin disk is only about 1,000 light-years thick, a tiny fraction of the disk's diameter. If you scaled Andromeda down so its disk was the size of a dinner plate, the disk would be thinner than a piece of paper. Despite its size, Andromeda is difficult to appreciate visually because its light is spread over a large area. The galaxy subtends an area in the sky about 6 times the diameter of the full moon. If it were brighter, if our eyes were more sensitive, it would appear as an enormous, elongated glow stretching across several degrees of the night sky. But because it's faint, we perceive only the brightest central region, a small fuzzy patch. Long-exposure photographs reveal the galaxy's full extent, showing the spiral arms, dust lanes, and outer halo. From a dark location with excellent conditions, experienced observers can sometimes see hints of the spiral structure with the naked eye, though most people see only the bright core. Andromeda is visible to the naked eye from dark locations. It's the most distant object visible without optical aid, a claim that's sometimes contested depending on how you define object. The Triangulum Galaxy, M33, also in the local group, is slightly more distant at about 2.7 to 3 million light-years, but is much fainter and harder to see. Under excellent conditions, some observers can spot it, but it's at the limit of naked-eye visibility. Andromeda, by contrast, is relatively easy to spot once you know where to look, appearing as a faint, fuzzy oval in the constellation Andromeda. The constellation is visible in the northern hemisphere in autumn and winter, high in the sky on evenings from September through January. To find the galaxy, locate the constellation Cassiopeia, which looks like a W or M depending on its orientation, and use it as a pointer toward Andromeda. The galaxy is about 15 to 20 degrees from Cassiopeia, near the constellation's brightest stars. With binoculars or a small telescope, the view improves dramatically, revealing the galaxy's elongated shape and bright core. Larger telescopes show more detail, dust lanes, spiral arms, star-forming regions. But Andromeda is so large that it's difficult to fit the entire galaxy into the field of view of high-magnification instruments. Wide-field telescopes or astrophotography capture the galaxy best, revealing its structure and beauty. Historically, Andromeda was known to ancient observers as a faint patch of light. Various cultures recorded it in their observations, though they had no idea what it was. The Persian astronomer Al-Sufi, as mentioned, called it a small cloud. European astronomers in the 17th and 18th centuries observed it with early telescopes and classified it as a nebula, a term used for any fuzzy object. Its true nature as a galaxy remained unknown until the 20th century. Andromeda is a barred spiral galaxy. Its structure includes a central bar-shaped concentration of stars, with spiral arms extending from the ends of the bar. This classification places it in the same category as the Milky Way, which is also a barred spiral. For many years, Andromeda was classified as an unbarred spiral, but observations in the early 2000s using infrared telescopes revealed the presence of a bar, albeit a relatively small one compared to the bars in some other galaxies. The bar is about 30,000 light-years long, composed of older, redder stars that have settled into orbits aligned along the bar. Bars form from gravitational instabilities in galactic disks. As stars orbit the galactic center, slight overdensities can grow, amplified by gravity, creating elongated structures. Once a bar forms, it can persist for billions of years, channeling gas toward the galactic center and influencing the formation of spiral arms. Bars are common in spiral galaxies. About 2/3 of spirals have them, suggesting they're a natural feature of galaxy evolution. The spiral arms themselves are density waves, regions where stars and gas temporarily bunch up as they orbit. The arms are not fixed structures made of the same stars. Rather, they're patterns that persist even as individual stars move through them. Think of them like traffic jams on a highway. The jam itself moves at a different speed than the cars passing through it, and the jam persists even as individual cars enter and exit. In Andromeda's spiral arms, star formation is enhanced by the compression of gas as it enters the arms, creating bright blue stars that highlight the arm's structure. These young, massive stars don't live long enough to move far from where they formed, so they trace out the spiral pattern. Andromeda has two main spiral arms. They're not as tightly wound as the Milky Way's arms and have a more open, looser structure. The arms contain young blue stars, star-forming regions, and large clouds of gas and dust. Between the main arms are several smaller arm segments and spurs, creating a complex structure that's not perfectly symmetric. This complexity is common in spiral galaxies and likely results from gravitational interactions with satellite galaxies and asymmetries in the distribution of mass. Andromeda's spiral structure is best observed in ultraviolet and infrared wavelengths. Ultraviolet light reveals hot, young stars in star-forming regions, tracing out the spiral arms. Infrared light penetrates dust clouds and reveals older stars and cooler dust, providing a different view of the galaxy's structure. Radio observations of neutral hydrogen show gas extending beyond the visible spiral arms, providing fuel for future star formation. The spiral arms are sites of active star formation, where gas clouds collapse under gravity to form new stars. The rate of star formation in Andromeda is modest by galactic standards, about 1 solar mass per year, similar to the Milky Way's rate. This is much lower than in starburst galaxies, which can form hundreds of solar masses of stars per year. Andromeda's relatively sedate star formation suggests it's a mature galaxy, having passed through more active periods earlier in its history. Much of the gas that could form stars has already been consumed, and what remains is being converted slowly. The merger with the Milky Way in the future will likely trigger a burst of star formation as gas clouds collide and are compressed. But for now, Andromeda is relatively quiet. Andromeda's disk is viewed at an angle of about 77 degrees from face-on. This orientation makes the galaxy appear elongated, like an oval or ellipse, rather than circular as it would appear if viewed face-on. The tilt is favorable for studying the galaxy's structure because we can see details in the spiral arms, star-forming regions, and dust lanes without the confusion of looking directly through the disk. If Andromeda were viewed edge-on, like the Sombrero Galaxy, M104, or the Needle Galaxy, NGC 4565, we would see it as a thin line with a central bulge, and much of its structure would be obscured by dust. If it were viewed face-on, like the Whirlpool Galaxy M51, we'd see the spiral arms spread out in a beautiful pattern, but we'd lose information about the vertical structure and thickness of the disk. The intermediate viewing angle of Andromeda provides a good compromise, allowing astronomers to study both the disk structure and the three-dimensional arrangement of stars and gas. The orientation also allows precise measurements of the galaxy's rotation. By observing the Doppler shifts of stars and gas on opposite sides of the galaxy, astronomers can determine how fast different regions are orbiting the galactic center. These rotation measurements reveal the distribution of mass, including dark matter, and provide insights into the galaxy's dynamics and evolution. The tilt angle has been measured precisely using various techniques, including observations of the motions of stars and gas, the shapes of features in the disk, and geometric modeling. The consensus value is about 77 degrees from face-on, or about 13 degrees from edge-on, with some uncertainty depending on exactly which part of the galaxy is measured. Andromeda has a double nucleus. When observed at high resolution, the galaxy's center shows not one peak of light, but two, separated by about 5 light-years. This was a puzzle when first discovered because most galaxies have a single, concentrated nucleus. The double nucleus led to speculation that Andromeda might contain two supermassive black holes, perhaps the remnants of a past merger with another galaxy. However, more detailed observations revealed that only one of the two bright regions, designated P1, is the true center of the galaxy, where the supermassive black hole resides. The other bright region, P2, is a disk of old stars orbiting the true center. The disk is eccentric, meaning the stars follow elliptical orbits, and the concentration of stars creates a second peak of brightness offset from the true center. From our viewing angle, this creates the appearance of a double nucleus. The disk of stars at the center is relatively small, only about 400 light-years across, and contains older red stars. It formed from gas that settled into the central region and formed stars in the distant past. The exact mechanisms that created this structure are still being studied, but it's likely related to the history of mass accumulation at the galactic center and possibly past interactions or mergers with other galaxies. The true nucleus, P1, is the location of Andromeda's supermassive black hole, a gravitational monster that anchors the galaxy's center and influences the motions of stars and gas throughout the inner regions. The black hole's mass has been estimated from observations of the velocities of stars and gas near the center, which orbit faster in response to the black hole's gravity. Current estimates place the black hole's mass at about 100 to 200 million times the Sun's mass, somewhat more massive than the Milky Way's central black hole, Sagittarius A, which has a mass of about 4 million solar masses. However, the exact mass is uncertain, and some studies suggest there might be two supermassive black holes in Andromeda's center, left over from a past merger, though this is still debated. Andromeda's supermassive black hole is surprisingly quiet. Despite its enormous mass, the black hole is not actively accreting large amounts of matter, so it doesn't produce the intense radiation characteristic of active galactic nuclei or quasars. This makes Andromeda a normal or inactive galaxy in terms of its central black hole activity, similar to the Milky Way. Most of the time, supermassive black holes in the centers of galaxies are quiescent, not consuming matter at high rates. Occasionally, gas clouds or stars wander too close and are accreted, producing flares of radiation, but these events are infrequent. Astronomers have observed faint X-ray and radio emission from Andromeda's nucleus, indicating some activity, but it's orders of magnitude weaker than what would be seen if the black hole were actively feeding. The quiescence of Andromeda's central black hole is fortunate for any hypothetical life in the galaxy's inner regions, because an active nucleus would flood the surroundings with high-energy radiation, making planets inhospitable. The Milky Way's central black hole is similarly quiet, creating a relatively safe environment in the galactic habitable zone. However, both black holes may have been more active in the past, and they'll likely become active again in the future, particularly during the Milky Way-Andromeda merger, when vast amounts of gas will be funneled toward the centers of both galaxies, feeding the black holes and triggering bursts of activity. Simulations suggest the merger will create a spectacular active galactic nucleus as the two supermassive black holes settle toward the center of the merged galaxy and eventually merge themselves, releasing an enormous burst of gravitational waves. Andromeda contains about 450 globular clusters. These are ancient, spherical collections of stars orbiting in the galaxy's halo, gravitationally bound but not part of the main disk. Each globular cluster contains hundreds of thousands to millions of stars packed into a region only tens to a few hundred light-years across. The stars in globular clusters are old, typically 10 to 13 billion years, formed early in the galaxy's history. Andromeda has about 3 times as many globular clusters as the Milky Way, which has about 150 known clusters. The reason for this difference is not fully understood, but may be related to Andromeda's larger mass and more complex merger history. Globular clusters often form during galaxy mergers, as gas clouds collide and are compressed, triggering bursts of star formation. The stars in these bursts can remain gravitationally bound as the cluster settles into orbit around the galaxy. Andromeda's large number of globular clusters suggests it has experienced multiple mergers in its past, each adding clusters to the population. Observations of Andromeda's globular clusters reveal 2 distinct populations: metal-poor clusters, which are very old and likely formed during the galaxy's initial assembly, and metal-rich clusters, which are somewhat younger and may have formed during later episodes of star formation or were captured from merging satellite galaxies. The distribution of clusters in the halo also provides clues about the galaxy's structure and history. Clusters orbiting in the inner halo have different properties than those in the outer halo, suggesting they formed in different environments or at different times. Studying Andromeda's globular clusters helps astronomers understand the galaxy's formation and evolution, and provides insights into the properties of old stellar populations. Andromeda is surrounded by a massive halo of hot gas. This gas, extending far beyond the visible disk, is extremely tenuous, far more rarefied than the best vacuum achievable on Earth, but it contains a significant amount of mass, comparable to the mass of all the stars in the galaxy. The gas is hot, heated to temperatures of millions of degrees by energy from supernovae, stellar winds, and possibly by gravitational interactions as the galaxy accretes matter from its surroundings. The hot halo emits X-rays, which can be detected by space-based X-ray telescopes like Chandra and XMM Newton. Observations reveal that the halo is not uniform but has structure, with hotter and cooler regions, and it contains chemical elements heavier than hydrogen and helium, indicating that some of the gas was processed through stars and then expelled in supernova explosions or stellar winds. The halo plays an important role in the galaxy's ecology. It serves as a reservoir of gas that can cool and fall back onto the disk, replenishing the supply of gas for star formation. This accretion is essential for maintaining star formation over billions of years because galaxies consume their gas supply relatively quickly, within a few billion years if no new gas is added. The infall of gas from the halo, along with accretion from the intergalactic medium and minor mergers with small satellite galaxies, provides the fuel for ongoing star formation. The halo also affects the evolution of the galaxy by regulating the flow of energy and matter. Supernova explosions and stellar winds inject energy into the halo, heating it and driving outflows that can expel gas from the galaxy. This feedback process regulates star formation, preventing galaxies from converting all their gas into stars too quickly. Understanding the halo is crucial for understanding galaxy evolution, and Andromeda's proximity makes it an ideal laboratory for studying these processes. Andromeda has at least 14 known satellite galaxies. These are smaller galaxies orbiting Andromeda, bound by its gravity. The two largest and most prominent are M32 and M110, both visible in small telescopes near Andromeda. M32 is a compact elliptical galaxy, unusually dense for its size, with a mass of about 3 billion solar masses packed into a diameter of only about 6,500 light-years. It's one of the densest galaxies known and may be the stripped core of a larger galaxy that was tidally disrupted by a close encounter with Andromeda. M110, also called NGC 205, is a larger elliptical galaxy, about 17,000 light-years across, with a mass of about 10 billion solar masses. It shows signs of recent or ongoing star formation, unusual for an elliptical galaxy, which typically contain only old stars. The star formation in M110 might be triggered by interactions with Andromeda's gravitational field as the satellite orbits through the outskirts of the larger galaxy. In addition to M32 and M110, Andromeda has numerous dwarf satellite galaxies, most of them very faint and difficult to detect. These dwarfs contain only a few million to a few hundred million stars and have been discovered in surveys that carefully map the distribution of stars around Andromeda. Some of these dwarfs are being torn apart by Andromeda's tidal forces, creating streams of stars that wrap around the galaxy. These tidal streams are evidence of ongoing galactic cannibalism, where large galaxies grow by consuming smaller ones. Over billions of years, Andromeda has likely consumed dozens or even hundreds of small galaxies, adding their stars to its halo and disk. The Andromeda Milky Way collision will begin in about 4 billion years. This might sound like an immensely long time, and it is by human standards, but it's less than the current age of the solar system, and much less than the time remaining before the Sun exhausts its hydrogen fuel and becomes a red giant in about 5 billion years. So the collision will occur before the Sun dies, though long after humanity is likely gone or radically transformed. As Andromeda and the Milky Way approach each other, their mutual gravity will begin to distort both galaxies. The disks will warp and stretch, pulled by tidal forces. Stars will be flung out of the galaxies into long tidal tails, streams of stars extending for hundreds of thousands or even millions of light-years into space. These tails are common in galaxy collisions and can be seen in many interacting galaxy pairs observed by telescopes. The first close passage will occur when the galaxy's outer regions overlap. Because galaxies are mostly empty space, the stars themselves will almost never collide. Stellar collisions are extremely unlikely given the vast distances between stars. But the gas clouds in both galaxies will collide, and these collisions will compress the gas, triggering bursts of star formation. New stars will ignite by the billions, creating brilliant blue regions of young stars visible across intergalactic distances. This starburst phase will consume much of the remaining gas in both galaxies, forming stars at rates perhaps 10 or 100 times faster than the current rates. The galaxies will pass through each other, and their gravity will pull them back together for a second passage, then a third, each time mixing the stars and gas more thoroughly. Eventually, after multiple passages over hundreds of millions or even billions of years, the two galaxies will merge completely, their stars and gas mixed together into a single, larger galaxy. The merger will create an elliptical galaxy. The spiral structures of both the Milky Way and Andromeda will be destroyed in the collision. The orderly rotation of the disks will be disrupted by gravitational interactions, and the stars will be scattered into more random orbits. The result will be an elliptical galaxy, a smooth, featureless ball or ellipsoid of stars with no spiral arms, no disk, and little or no gas remaining for future star formation. Elliptical galaxies are thought to form primarily through major mergers, where two galaxies of comparable mass collide. Such mergers scramble the orbits of stars, erasing any pre-existing structures like disks and spiral arms. The merged galaxy, sometimes informally called Milkomeda or Milkdromeda, will be one of the larger elliptical galaxies in the local group, containing perhaps 2 trillion stars or more, the combined stellar populations of both progenitors, minus the stars flung out into tidal tails. The merged galaxy will also contain 2 supermassive black holes, at least initially. The black holes from the centers of the Milky Way and Andromeda will spiral toward each other as the galaxies merge, losing energy to gravitational interactions with surrounding stars. Eventually, the black holes will merge, coalescing into a single, more massive black hole with perhaps 150 to 250 million solar masses. This merger will produce a powerful burst of gravitational waves, rippling across the universe at the speed of light. Unfortunately, no human-built gravitational wave detectors will be around to observe it, assuming humanity doesn't survive or transcend in some form to witness the event. The black hole merger will occur relatively late in the process, perhaps 1 billion years after the galaxies first collide, because it takes time for the black holes to lose enough orbital energy to come together. The Sun and Solar System will probably survive the merger. Despite the violence of a galactic collision, individual stars are so far apart that direct collisions are incredibly unlikely. The average distance between stars in the Milky Way is about 5 light-years, while stars themselves are typically only a few light-seconds across. The ratio of the distance between stars to the size of stars is enormous, comparable to the ratio between the distance between cities and the size of individual people. If you think of stars as people standing in different cities across a continent, the chance of 2 people randomly colliding as the continents merge is vanishingly small. The same applies to stars in a galaxy merger. The Sun will almost certainly not collide with another star. However, the Sun's orbit will change dramatically. Gravitational interactions during the merger will perturb the orbits of stars, flinging some into the outer halo or even ejecting them from the galaxy entirely, while others settle into new orbits closer to the center. Simulations suggest the Sun has about a 50% chance of ending up in the outer regions of the merged galaxy, perhaps twice as far from the center as it is now, and about a 10% chance of being ejected from the galaxy entirely, becoming a wandering star in intergalactic space. Even if the Sun remains within the merged galaxy, its new orbit will likely be very different from its current nearly circular orbit in the Milky Way's disk. It might end up on a highly elliptical orbit, plunging through the center and then swinging out to the halo. Earth and the other planets will remain bound to the Sun. The distances within the solar system are so small compared to the distances between stars that the solar system will remain intact. But the night sky from Earth will be dramatically different. The familiar Milky Way band will be gone, replaced by the smooth glow of an elliptical galaxy's stellar distribution. The night sky during the merger will be spectacular. Long before the galaxies actually collide, Andromeda will grow larger and brighter in Earth's sky. Currently, Andromeda appears as a faint, fuzzy oval about 6 times the Moon's diameter, visible only from dark locations. As it approaches over millions of years, it will grow steadily larger and brighter, becoming visible even from light-polluted cities. In a few 100 million years, Andromeda will dominate the night sky, appearing as an enormous glowing structure stretching across tens of degrees. During the first close passage, about 4 billion years from now, the sky will be filled with 2 great spirals, Andromeda and the Milky Way, distorted and intertwined, with streams of stars connecting them. New star-forming regions, blazing with the light of millions of young stars, will light up the gas clouds compressed by the collision. The sky will be brighter, with more stars visible than at any time in Earth's history. Of course, by this time, Earth may no longer be habitable. The Sun will be about 40% more luminous than it is today, having gradually brightened over billions of years. This increased luminosity will heat Earth, evaporating the oceans and creating a runaway greenhouse effect. Complex life will likely be extinct by the time of the collision, and the planet may resemble Venus, with a thick, hot atmosphere and a scorched surface. But if intelligent observers somehow existed, perhaps on a planet farther from the Sun, or on a moon or space station, they would witness one of the most spectacular astronomical events imaginable, a collision of galaxies playing out over hundreds of millions of years. Andromeda has experienced past mergers. Evidence from observations of its stellar halo and globular cluster populations suggests Andromeda has collided with and consumed smaller galaxies multiple times in its history. One major merger likely occurred about 2 billion years ago, when a galaxy perhaps 1/4 of Andromeda's mass collided with it. This merger would have disrupted Andromeda's disk, creating the thickened disk and complex stellar halo observed today. Stars from the merging galaxy were scattered throughout Andromeda, and the event probably triggered bursts of star formation as gas clouds collided. Evidence for this past merger includes the presence of tidal streams, long, arcing structures of stars in the halo that trace the orbits of disrupted satellite galaxies. The most prominent is the giant stellar stream, a vast arc of stars extending across the halo, likely the remnant of a dwarf galaxy that was torn apart by Andromeda's gravity. Other streams have been detected as well, each representing a past or ongoing merger. Andromeda's globular cluster system also bears the signature of mergers. Some clusters have chemical compositions and kinematics, their motions through space, that suggest they didn't form in Andromeda but were captured from other galaxies. By studying the ages, compositions, and orbits of these clusters, astronomers can reconstruct Andromeda's merger history, piecing together a story of growth through accretion. Galaxy mergers are a key part of galaxy evolution. Most large galaxies, including the Milky Way and Andromeda, grew to their current sizes by merging with smaller galaxies over billions of years. The early universe contained many small galaxies, and these gradually merged into larger ones through hierarchical assembly, a process predicted by models of structure formation in a universe dominated by dark matter. Andromeda's disk has a warp. When observed in neutral hydrogen gas using radio telescopes, the disk shows a clear departure from flatness, particularly in the outer regions. One side of the disk is tilted upward relative to the galactic plane, while the other side is tilted downward, creating an S-shaped warp when viewed edge-on. This warp extends to large distances from the galactic center, out to at least 100,000 light-years, well beyond the visible stellar disk. Warps are common in spiral galaxies. The Milky Way has one too, and they're thought to be caused by gravitational interactions with satellite galaxies. As satellites orbit through the halo, their gravity tugs on the disk, pulling it out of the plane. The warp propagates through the disk like a wave, and because the outer parts of the disk rotate more slowly, the warp persists there longer. Andromeda's warp may be caused by its satellite galaxies, particularly M33, the Triangulum Galaxy, which orbits at a distance and may have passed close to Andromeda in the past. Alternatively, the warp could be caused by the gravitational influence of the Milky Way itself, as the two galaxies orbit each other in the local group. Detailed simulations are needed to determine the exact cause, and researchers are actively studying Andromeda's warp to understand the dynamics of galaxy interactions. The warp affects the distribution of gas in the galaxy and may influence star formation in the outer disk, where gas densities are low and star formation is less active. Andromeda is receding from most other galaxies. This might seem contradictory given that it's approaching the Milky Way, but both facts are true. The universe is expanding, and galaxies that are not gravitationally bound to each other are being carried apart by the expansion of space. Andromeda and the Milky Way are part of the local group, a gravitationally bound structure where the mutual gravity of the galaxies overcomes the expansion of the universe. Within the local group, galaxies move according to their gravitational interactions, not the expansion of space. But galaxies outside the local group, not bound to it by gravity, are receding from us due to cosmic expansion. From Andromeda's perspective, distant galaxies are receding, just as they are from our perspective. The expansion of the universe is a property of space itself, not the motion of galaxies through space. Space stretches, carrying galaxies apart, except where gravity is strong enough to bind them together. On the scale of galaxy clusters and superclusters, gravity can bind hundreds or thousands of galaxies, but beyond these scales, expansion dominates. The local group is part of the larger Virgo supercluster, a collection of galaxy groups and clusters spanning about 110 million light-years. The Virgo supercluster itself is part of an even larger structure called Laniakea, which includes about 100,000 large galaxies and spans about 520 million light-years. Within Laniakea, galaxies are moving toward a central region called the Great Attractor, pulled by the combined gravity of mass concentrations in that direction. But at scales larger than superclusters, the expansion of the universe dominates, and structures are being carried apart, with more distant structures receding faster in accordance with Hubble's law. Andromeda contains about 7 billion solar masses of gas and dust. This is the raw material for future star formation, though it's only a small fraction of the galaxy's total mass. which is dominated by stars and dark matter. The gas is mostly hydrogen, with some helium and trace amounts of heavier elements produced by previous generations of stars. The dust consists of tiny grains of carbon, silicates, and other minerals formed in the atmospheres of aging stars and in supernova explosions. The gas and dust are distributed throughout the disk, concentrated in the spiral arms where star formation occurs. The gas exists in multiple phases: cold molecular clouds where stars form, with temperatures around 10 to 20 Kelvin, warm neutral atomic hydrogen, with temperatures around 100 to 1000 Kelvin, warm ionized gas, heated by ultraviolet radiation from young stars, and hot ionized gas in the halo, with temperatures of millions of degrees. Each phase plays a role in the galaxy's ecology. The cold molecular clouds are the densest regions, where gravity can overcome internal pressure and cause collapse, forming new stars. The warm atomic hydrogen serves as a reservoir that can cool and condense into molecular clouds. The warm ionized gas is heated by stellar radiation and supernova shocks, and it eventually cools and recycles back into the cold phase. The hot halo gas, as mentioned earlier, can cool and fall back onto the disk, replenishing the gas supply. The amount of gas in Andromeda is similar to that in the Milky Way. Both galaxies, having consumed much of their original gas, supply over billions of years of star formation. The remaining gas will be consumed in the next few billion years if no new gas is added. However, the merger with the Milky Way will bring new gas into the system, as the gas reserves of both galaxies are combined and compressed, triggering a final burst of star formation that will consume most of the remaining gas. Andromeda has a prominent ring of star formation. Located about 10,000 light-years from the center, this ring is a region where star formation is particularly active, producing young, hot stars that emit ultraviolet light. The ring was discovered in the 1980s using ultraviolet observations from space-based telescopes. It's not a perfectly circular ring, but rather an elliptical or even double-ring structure, with star formation occurring in discrete regions along the ring. The ring's origin is debated. One hypothesis is that it formed from gas that was pushed outward by a past merger or interaction, creating a shock front where gas compressed and formed stars. Another hypothesis is that the ring is a resonance feature, created by the gravitational influence of the bar or spiral density waves, which channel gas into particular orbits where conditions favor star formation. Resonances occur at specific radii, where the orbital periods of gas clouds match the pattern speed of the bar or spiral arms, causing gas to pile up and compress. The ring structure is not unique to Andromeda. Many barred spiral galaxies have rings of star formation at certain radii, often at resonance locations. Studying these rings helps astronomers understand the dynamics of gas in galaxies and the processes that trigger star formation. Andromeda's ring is particularly prominent and has been studied extensively, serving as a laboratory for testing theories of star formation and galactic structure. The ring contains numerous star clusters and associations, collections of young stars that form together from the same gas cloud. These clusters are gradually dispersing as the stars age and their orbits carry them away from the ring, but while they're young, they trace out the ring's structure and provide information about the rate and history of star formation. Andromeda is moving through the intergalactic medium. Like all galaxies, Andromeda is not stationary in space, but moves through the tenuous gas that fills the space between galaxies. This motion creates a bow shock, similar to the shock wave created by a boat moving through water or a supersonic jet moving through air. As Andromeda moves, it pushes aside the intergalactic gas, compressing it and heating it. The compressed gas forms a shock front ahead of the galaxy, and some of the gas may be swept away in a wake behind the galaxy. Observations in X-rays reveal the hot gas around Andromeda and provide clues about its motion through the intergalactic medium. The interaction between the galaxy and the surrounding gas can affect the galaxy's evolution. Gas can be stripped from the galaxy by ram pressure as it plows through the intergalactic medium, particularly in the outer regions where the galaxy's gravity is weakest. This process, called ram pressure stripping, is more significant in dense environments like galaxy clusters, where the intergalactic medium is denser and galaxies move faster. In the local group, the intergalactic medium is tenuous, and ram pressure stripping is less important, but it still occurs to some extent. The motion of Andromeda through the intergalactic medium also affects the distribution of its hot halo gas, creating asymmetries and possibly triggering accretion of intergalactic gas onto the galaxy, providing new fuel for star formation. Andromeda's rotation curve is flat. This is one of the key pieces of evidence for dark matter. A rotation curve shows how fast objects orbit at different distances from the galactic center. In the solar system, planets farther from the Sun orbit more slowly, following Kepler's laws. If galaxies worked the same way, with most of their mass concentrated at the center, stars in the outer regions should orbit more slowly than stars closer in. But observations of Andromeda and other spiral galaxies show that stars in the outer regions orbit at roughly the same speed as stars closer to the center. The rotation curve is flat, not declining. This can only be explained if there's additional, unseen mass distributed throughout the galaxy and extending far beyond the visible disk. This unseen mass is dark matter, which doesn't emit, absorb, or reflect light, but exerts gravitational force. Andromeda's flat rotation curve was measured using observations of the Doppler shifts of stars and gas at various distances from the center. By measuring how fast material is moving toward or away from us, astronomers can determine its orbital velocity. The flat rotation curve indicates that dark matter makes up the majority of Andromeda's mass, perhaps 85% to 90% of the total. The dark matter is distributed in a roughly spherical halo, extending well beyond the visible galaxy, out to distances of perhaps 500,000 light-years or more. This dark matter halo dominates the galaxy's gravitational field and influences the motions of stars, gas, and satellite galaxies. Understanding dark matter remains one of the biggest challenges in astrophysics, and studying galaxies like Andromeda provides crucial data for testing theories and models. Andromeda is part of the local group. This is a collection of about 80 known galaxies bound together by gravity, spanning a region about 10 million light-years across. The local group is dominated by two large galaxies, Andromeda and the Milky Way, which together contain most of the group's stellar mass. The third largest member, the Triangulum Galaxy, M33, is much smaller, with perhaps 1/10 the stellar mass of Andromeda. The rest of the local group consists of dwarf galaxies, most of them elliptical or irregular in shape, containing a few million to a few billion stars. Many of these dwarfs are satellites of either the Milky Way or Andromeda, orbiting the larger galaxies. The local group is gravitationally isolated from other galaxy groups, meaning that its member galaxies are bound to each other and not being pulled toward other massive structures by gravity. This isolation makes the local group a relatively simple system to study, free from the complexities of dense environments like galaxy clusters. The local group is part of the larger Virgo supercluster, but it's located in the outskirts, in a relatively underdense region. The Virgo supercluster itself is part of Laniakea, a vast supercluster containing about 100,000 large galaxies. But within Laniakea, the local group is a minor structure, a small collection of galaxies in a backwater region far from the major centers of mass. The ultimate fate of the local group is to merge into a single structure. Over billions of years, most of the dwarf galaxies will be consumed by Andromeda and the Milky Way, and eventually, Andromeda and the Milky Way themselves will merge. Triangulum may also merge with one of the two large galaxies or be ejected from the group during the Andromeda-Milky Way collision. The end result, billions of years from now, will be a single large elliptical galaxy, the remnant of the entire local group. Andromeda's age is about 10 billion years. This estimate is based on the ages of its oldest stars, which are about 10 to 13 billion years old, comparable to the oldest stars in the Milky Way. The galaxy formed not long after the Big Bang, which occurred about 13.8 billion years ago. Like most large galaxies, Andromeda formed through the hierarchical assembly of smaller structures. In the early universe, matter was distributed almost uniformly, with only tiny density fluctuations, slight overdensities where matter was slightly more concentrated. These overdensities, amplified by gravity, grew over time, pulling in more matter and forming the first small galaxies. These proto-galaxies contain the first stars, formed from primordial gas with almost no heavy elements. Over time, these small galaxies merged, building larger galaxies. Andromeda likely formed from the merger of several smaller galaxies, each contributing stars and gas to the growing structure. As the galaxy grew, it settled into a disk, with gas falling into the plane and forming stars in the rotating disk. The oldest stars in Andromeda's halo are remnants of this early epoch, formed before the disk settled. The disk stars are younger, formed after the galaxy's structure stabilized. Andromeda has continued to evolve through accretion, consuming smaller satellites and occasionally undergoing major mergers that disrupted the disk and triggered bursts of star formation. The galaxy we see today is the product of 10 billion years of evolution, shaped by gravity, star formation, mergers, and the influence of dark matter. Andromeda has a supermassive black hole binary, or possibly two separate black holes. Observations of the motions of stars and gas near Andromeda's center suggest the presence of more than one compact, massive object. If confirmed, this would indicate that Andromeda's central black hole is actually two black holes orbiting each other, likely the remnant of a past merger where a smaller galaxy with its own supermassive black hole fell into Andromeda. The two black holes would be spiraling toward each other, losing energy through gravitational interactions with surrounding stars and gas, a process that can take hundreds of millions or even billions of years. Eventually, they would merge, coalescing into a single, more massive black hole and releasing a burst of gravitational waves. Binary supermassive black holes are expected to be common in galaxies that have experienced major mergers, but they're difficult to detect because the black holes themselves are invisible and can only be inferred from their gravitational effects. The evidence for a binary in Andromeda is not yet conclusive. Alternative explanations for the observed motions exist. But if confirmed, it would be one of the closest examples of a supermassive black hole binary, providing a valuable opportunity to study these systems. Binary supermassive black holes are also of interest because their eventual mergers produce gravitational waves at very low frequencies, too low for ground-based detectors like LIGO, but potentially detectable by future space-based detectors like LISA, Laser Interferometer Space Antenna, planned for launch in the 2030s. Detecting gravitational waves from merging supermassive black holes would open a new window into understanding galaxy evolution and the growth of black holes. Triangulum, the third largest member of the local group, may be a satellite of Andromeda. M33, also known as the Triangulum Galaxy, is about 2.7 to 3 million light-years from Earth and about 750,000 light-years from Andromeda. For years, it was unclear whether Triangulum was orbiting Andromeda, making it a satellite, or whether it was an independent member of the local group on a different trajectory. Recent measurements of Triangulum's motion through space, obtained using the Hubble Space Telescope and other instruments, suggest it may be gravitationally bound to Andromeda, orbiting the larger galaxy at a great distance. If this is true, Triangulum is by far the largest satellite galaxy of Andromeda and one of the largest satellite galaxies known around any galaxy. The orbital period would be extremely long, perhaps several billion years, and Triangulum may be on its first orbit, having been captured by Andromeda's gravity relatively recently. Alternatively, Triangulum might be on a close pass but not bound, in which case it would eventually escape Andromeda's gravitational influence and move off into intergalactic space. Simulations of the local group's evolution suggest that Triangulum will likely interact with Andromeda or the Milky Way during the upcoming merger. It might collide with one of them, be captured, or be ejected from the local group by the gravitational chaos of the collision. The exact outcome depends on Triangulum's current orbit and velocity, which are still being refined by observations. Andromeda's disk contains old stars as well as young ones. While the spiral arms are dominated by young, blue stars formed within the last few 100 million years, the disk also contains older populations of stars formed billions of years ago. These older stars are redder and cooler, having exhausted much of their fuel and expanded into red giants or settled into stable phases as red dwarfs. The presence of multiple stellar populations, stars of different ages and chemical compositions, reflects the ongoing process of star formation over billions of years. The oldest disk stars are nearly as old as the galaxy itself, formed when Andromeda's disk first settled. Intermediate-age stars formed during periods of moderate star formation. The youngest stars formed recently in the spiral arms. By studying the ages and compositions of stars in different parts of Andromeda, astronomers can reconstruct the galaxy's star formation history, determining when and where star formation was most active. This is done using spectroscopy, analyzing the light from stars to determine their temperatures, compositions, and ages. Stars with lower abundances of heavy elements, metals, in astronomical parlance, are older, formed when the galaxy was young and had not yet been enriched by supernovae. Stars with higher metal abundances are younger, formed from gas enriched by previous generations of stars. The radial distribution of stellar ages and metallicities provides clues about how the disk formed and evolved, whether it formed quickly from a collapsing gas cloud or gradually through the accretion of smaller structures. Andromeda is one of the few galaxies approaching us. Most galaxies show redshifts in their spectra, indicating they're moving away from us due to the expansion of the universe. but about 100 galaxies in the local group show blue shifts, indicating they're approaching. These are all gravitationally bound to the local group, their motions dominated by gravity rather than cosmic expansion. Andromeda is the largest and most massive of the blue-shifted galaxies, and its approach is the most significant for the Milky Way's future. Among the other blue-shifted galaxies are several dwarf satellites of the Milky Way and Andromeda, along with Triangulum and a few other small members of the local group. Beyond the local group, almost all galaxies are redshifted, receding from us. The nearest large galaxy cluster, the Virgo cluster, is about 54 million light-years away and receding at about 1,100 kilometers per second. The Coma cluster, about 300 million light-years away, is receding at about 7,000 kilometers per second. The relationship between distance and recession velocity, Hubble's law, reveals the expansion of the universe, one of the most important discoveries in astronomy. The fact that Andromeda is approaching, despite this expansion, underscores the importance of local gravity in determining the motions of nearby galaxies. Andromeda's stellar halo extends far beyond the visible disk. Stars in the halo are scattered throughout a vast region, some detected at distances of over 500,000 light-years from the galactic center. This is nearly 5 times the diameter of the visible disk and comparable to the distance between Andromeda and the Milky Way. The halo is extremely tenuous. The density of stars is very low, but it contains a significant number of stars, perhaps 10% to 20% of Andromeda's total stellar mass. The halo stars are old and metal-poor, formed early in the galaxy's history or captured from satellite galaxies that were disrupted by tidal forces. The structure of the halo is complex, with tidal streams, shells, and other features that trace the orbits and remnants of past mergers. Mapping the halo provides insights into Andromeda's merger history and the process of hierarchical galaxy assembly. The halo also contains dark matter, which dominates the mass at large distances from the center. The dark matter halo extends even farther than the stellar halo, perhaps to distances of 1 million light-years or more, far beyond where any stars or gas can be detected. The extent of the dark matter halo is inferred from the motions of satellite galaxies and from models of galaxy formation. The halo's mass determines the orbital velocities of satellites and influences the dynamics of the entire local group. Andromeda has been studied for centuries, but much of our knowledge is recent. Ancient and medieval astronomers observed Andromeda as a faint nebula, but they had no understanding of what it was. Early telescopic observations in the 17th and 18th centuries revealed its extended structure, but couldn't resolve individual stars. In the 19th century, improved telescopes showed hints of spiral structure, and astronomers debated whether spiral nebulae were gaseous clouds in the Milky Way or distant island universes. The debate was settled in the 1920s by Edwin Hubble's discovery of Cepheid variables in Andromeda, proving it was a separate galaxy. Since then, Andromeda has been studied extensively across the electromagnetic spectrum, from radio waves to gamma rays. The Hubble Space Telescope, launched in 1990, has provided some of the most detailed images of Andromeda, resolving individual stars and star clusters and revealing the galaxy's structure in unprecedented detail. The Spitzer Space Telescope, an infrared observatory, mapped Andromeda's dust and star formation. The Chandra X-ray Observatory studied X-ray sources in the galaxy, including X-ray binaries, supernova remnants, and the hot halo gas. Ground-based telescopes have mapped Andromeda's neutral hydrogen gas, measured the motions of stars and gas to study the galaxy's dynamics, and conducted surveys to discover faint stars in the halo and satellite galaxies. Future observations with next-generation telescopes, including the James Webb Space Telescope and the upcoming Extremely Large Telescope, will continue to reveal Andromeda's secrets, providing even more detailed views of its structure, stellar populations, and history. Andromeda's chemical composition is similar to the Milky Way's. Both galaxies have undergone billions of years of star formation, and both have been enriched by supernovae and stellar winds that scatter heavy elements into the interstellar medium. The abundances of elements like carbon, oxygen, nitrogen, iron, and others are comparable in both galaxies, reflecting similar histories of stellar evolution. However, there are subtle differences. Andromeda's inner regions are slightly more metal-rich than the Milky Way's inner regions, possibly due to differences in star formation history or gas accretion rates. The outer regions of both galaxies are less metal-rich. As is typical for spiral galaxies, metallicity decreases with distance from the center because star formation is less active in the outer disk and gas is less enriched. Studying the chemical compositions of stars in Andromeda through spectroscopy provides information about the galaxy's history. Stars that formed early in the galaxy's history have lower metallicities, while stars that formed more recently have higher metallicities, reflecting the gradual enrichment of the interstellar medium over time. By measuring metallicities as a function of stellar age and location, astronomers can reconstruct the history of star formation and gas flows in the galaxy. The similarity in chemical compositions between Andromeda and the Milky Way suggests that the processes governing galaxy evolution are similar in both galaxies, despite their somewhat different masses and merger histories. Andromeda's star formation rate is about 1 solar mass per year. This is the rate at which gas is being converted into new stars, measured by observing the light from young stars and star-forming regions and estimating the mass of stars being formed. The rate is similar to the Milky Way's, both galaxies forming stars at a modest pace compared to starburst galaxies, which can form hundreds of solar masses of stars per year. The relatively low star formation rate indicates that Andromeda is a mature galaxy, having consumed much of its gas over billions of years. The remaining gas is being converted into stars slowly, and the galaxy is gradually fading as older stars evolve and die, and fewer new stars are formed to replace them. This process will continue for billions of years. Eventually, most of the gas will be consumed, and star formation will cease almost entirely. The galaxy will be dominated by old red stars, red dwarfs that burn for trillions of years, and the remnants of higher-mass stars, white dwarfs, neutron stars, and black holes. This is the eventual fate of all spiral galaxies that don't undergo major mergers or accrete large amounts of new gas. The merger with the Milky Way will temporarily reverse this trend, as the collision compresses gas and triggers a burst of star formation. But once the burst ends and the gas is exhausted, star formation will decline to very low levels in the merged galaxy. Andromeda's bulge is large and prominent. The central bulge is a dense, roughly spherical concentration of stars extending several thousand light-years from the center. Bulges are common in spiral galaxies and are thought to form through a combination of processes. The settling of gas toward the center early in the galaxy's history, the accumulation of stars through mergers, and dynamical processes like bar-driven gas inflows that funnel material toward the center. Andromeda's bulge contains primarily old, red stars, indicating it formed early in the galaxy's history. The bulge's size and mass are intermediate between small classical bulges, which form through mergers, and large pseudobulges, which form through secular evolution driven by bars and disk instabilities. Some studies suggest Andromeda's bulge might be a composite, containing both classical and pseudobulge components. The bulge rotates, though not as rapidly as the disk, and its stars have higher velocity dispersions. They move more randomly rather than following orderly circular orbits. This higher dispersion indicates the stars in the bulge have more random motions, a signature of dynamical heating caused by gravitational interactions. The bulge also has a higher metallicity than the disk, reflecting its higher star formation rate and efficiency at converting gas into stars early in the galaxy's history. Studying the bulge provides insights into the early phases of galaxy formation and the processes that build the central regions of galaxies. Andromeda contains X-ray binaries. These are systems where a compact object, a neutron star or black hole, is accreting matter from a companion star. The infalling matter heats up to millions of degrees as it spirals toward the compact object, emitting intense X-rays. Andromeda contains dozens to hundreds of X-ray binaries, detected by X-ray observatories like Chandra and XMM Newton. These systems provide information about the population of compact objects in the galaxy and the physics of accretion. Some X-ray binaries are high-mass systems, where the companion is a massive, short-lived star. These systems are young, typically found in star-forming regions where massive stars exist. Other X-ray binaries are low-mass systems, where the companion is a low-mass star like a red dwarf or even a white dwarf. These systems can be old, having formed billions of years ago, because the low-mass companion has a long lifetime. Studying X-ray binaries in Andromeda allows astronomers to test models of binary evolution, accretion physics, and the formation of compact objects. The number and properties of X-ray binaries depend on the star formation history of the galaxy, the initial mass function, the distribution of stellar masses at birth, and the dynamical environment. Globular clusters, for example, have high stellar densities, leading to frequent interactions between stars that can form X-ray binaries through dynamical captures. Several of Andromeda's X-ray binaries are located in globular clusters, consistent with this picture. Andromeda has supernova remnants. When massive stars explode as supernovae, they leave behind expanding shells of hot gas, supernova remnants. These remnants are visible in X-rays, radio waves, and sometimes in optical light, appearing as glowing, filamentary structures. Andromeda contains dozens of known supernova remnants detected through surveys at various wavelengths. Studying these remnants provides information about the rate of supernovae in the galaxy, the energy and dynamics of supernova explosions, and the chemical enrichment of the interstellar medium. Supernova remnants expand outward at speeds of thousands to tens of thousands of kilometers per second, sweeping up surrounding gas and compressing it. The shock front created by the expansion heats the gas to millions of degrees, causing it to emit X-rays. Over time, the remnant slows down as it sweeps up more mass, and eventually, after tens of thousands of years, it merges with the surrounding interstellar medium, dispersing the heavy elements created in the supernova. The rate of supernovae in Andromeda is about 1 or 2 per century, based on estimates from the number of massive stars and the expected supernova rate. However, directly observing a supernova in Andromeda is rare because supernovae are brief events, lasting only weeks to months at peak brightness. The last confirmed supernova in Andromeda was observed in 1885, designated S Andromeda or SN 1885A. It reached a peak magnitude of about 6, visible to the naked eye, making it the first supernova observed beyond the Milky Way, though at the time astronomers didn't know Andromeda was a separate galaxy. It was initially thought to be a nova, a much less energetic event, and only later recognized as a supernova. Andromeda's outer disk is actively forming stars. While the spiral arms are the primary sites of star formation also occurs in the outer disk, beyond the main spiral structure, at radii of 50,000 to 100,000 light-years or more from the center. This extended star formation is somewhat surprising because the outer disk has low gas densities, and conventional models of star formation predict it should be difficult for gas to collapse and form stars in such diffuse conditions. However, observations reveal numerous young stars and star clusters in the outer disk, indicating ongoing star formation. The process is not as efficient as in the spiral arms, but it's happening. One possible explanation is that the outer disk is more susceptible to instabilities that can trigger collapse, or that past interactions with satellite galaxies or gas accretion events have compressed gas in the outer regions, creating conditions favorable for star formation. Another possibility is that star formation in the outer disk occurs in localized bursts, with clumps of gas collapsing episodically rather than continuously. Understanding star formation in the outer disks of galaxies is an active area of research, with implications for galaxy evolution and the distribution of stellar populations. Andromeda's proximity makes it an ideal laboratory for studying this process, and observations continue to reveal details of star formation in the outer disk. Andromeda's magnetic field has been mapped. Using radio observations of polarized emission from cosmic rays spiraling in magnetic fields, astronomers have traced the structure of Andromeda's magnetic field. Like the Milky Way, Andromeda has a large-scale magnetic field aligned with the spiral arms. The field strength is a few microgauss, about 1,000,000 times weaker than Earth's magnetic field at the surface, but comparable to the Milky Way's field. The magnetic field plays an important role in the interstellar medium, affecting the motion of charged particles, the dynamics of gas clouds, and the process of star formation. Magnetic fields provide support against gravitational collapse, so gas clouds need to overcome magnetic pressure as well as thermal pressure to collapse and form stars. The field also channels cosmic rays, high-energy particles produced by supernovae and other energetic events, influencing their distribution and interactions with the interstellar medium. The origin and maintenance of galactic magnetic fields are still not fully understood. They're likely generated and amplified by dynamo processes, where the motion of charged particles, driven by turbulence, differential rotation, and other processes, creates electric currents that generate magnetic fields. These fields are then stretched and twisted by the galaxy's rotation, creating the large-scale structure observed. Andromeda's magnetic field, like the Milky Way's, provides a laboratory for studying these processes and testing dynamo theory. Andromeda has a complex dust distribution. Dust, tiny solid particles of carbon, silicates, and other materials, is distributed throughout the galaxy's disk, particularly concentrated in the spiral arms and star-forming regions. Dust absorbs and scatters light, creating dark lanes visible in optical images of the galaxy. These lanes trace the spiral structure and highlight regions where gas and dust are densest. Observations in infrared wavelengths, which can penetrate dust, reveal the distribution of dust and the cooler stars hidden behind it. The Spitzer Space Telescope, an infrared observatory, mapped Andromeda's dust in detail, showing that the dust closely follows the distribution of gas and star-forming regions. The dust emission also reveals the temperature of the dust, which is heated by starlight. Dust plays several important roles in the galaxy. It shields the interiors of gas clouds from ultraviolet radiation, allowing them to cool and collapse to form stars. Dust grains also serve as surfaces where molecules can form, particularly molecular hydrogen, which is the primary fuel for star formation. Without dust, the efficiency of star formation would be much lower. Dust also affects the appearance of the galaxy, dimming and reddening light that passes through it. Astronomers must account for dust when studying the properties of stars and star-forming regions, correcting for the absorption and scattering caused by intervening dust. Andromeda's satellites are being tidally disrupted. As satellite galaxies orbit Andromeda, tidal forces, differences in gravitational pull across the satellite, stretch and distort them. Over time, stars are pulled from the satellites, forming tidal streams that trace the satellite's orbits. Several prominent tidal streams have been discovered in Andromeda's halo, the remnants of dwarf galaxies that were torn apart by Andromeda's gravity. The giant stellar stream, mentioned earlier, is the most prominent, a vast arc of stars stretching across the halo. Other streams are more subtle, requiring careful analysis of star counts and distributions to detect. By studying these streams, their positions, velocities, and chemical compositions, astronomers can reconstruct the orbits of the disrupted satellites and learn about their properties and the structure of Andromeda's dark matter halo. The streams also provide evidence for the hierarchical assembly of galaxies, showing that large galaxies grow by consuming smaller ones. The process of tidal disruption is ongoing. Some of Andromeda's current satellites, like M32 and M110, show signs of tidal disturbances, with their shapes and distributions of stars indicating they've been affected by Andromeda's gravity. Eventually, these satellites may be completely disrupted and absorbed into Andromeda's halo, their stars scattered throughout the larger galaxy. Andromeda's stellar density decreases with distance from the center. This is typical for galaxies. The central regions are densely packed with stars, while the outer regions are sparsely populated. In Andromeda's core, the stellar density is tens of thousands of stars per cubic light-year. If Earth were located there, the night sky would be filled with bright stars, thousands of them brighter than Sirius, the brightest star in Earth's current night sky. The sky would never be truly dark. In the outer disk, the stellar density drops to less than 1 star per cubic light-year, similar to the solar neighborhood in the Milky Way. In the halo, the density is even lower, perhaps 0.001 stars per cubic light-year or less. Despite the lower density, the halo contains a significant number of stars because it covers such a vast volume. The radial density profile of Andromeda follows a mathematical form called a Sayesic profile, which describes how surface brightness and stellar density decrease with radius. The exact shape of the profile depends on the component being measured. The bulge, disk, and halo each have different profiles. By fitting models to the observed surface brightness, astronomers can determine the galaxy's structure and the distribution of mass, including dark matter. Andromeda is moving toward the Virgo cluster. While Andromeda is approaching the Milky Way within the local group, the local group as a whole is moving toward the Virgo cluster, a large concentration of over 1,000 galaxies about 54 million light-years away. The Virgo cluster's gravity is pulling the local group toward it at about 200 to 300 kilometers per second. This motion is separate from the expansion of the universe and reflects the gravitational influence of massive structures on their surroundings. The Virgo cluster is the nearest large galaxy cluster and is part of the larger Virgo supercluster, a vast structure spanning about 110 million light-years that contains the local group and several other galaxy groups and clusters. Recent studies have refined our understanding of these large-scale structures. The Virgo supercluster, it turns out, is part of an even larger structure called Laniakea, which spans about 520 million light-years and contains about 100,000 large galaxies. Laniakea is defined not by the positions of galaxies, but by their motions. All galaxies within Laniakea are moving toward a central region called the Great Attractor, a concentration of mass whose exact nature is still being studied. The motion of the local group toward the Virgo cluster is part of this larger flow of galaxies within Laniakea. Understanding these motions helps astronomers map the distribution of mass in the universe, including dark matter, and provides insights into the large-scale structure of the cosmos. Andromeda's outer halo contains very old stars. Some of the stars in the outer halo are among the oldest in the universe, with ages of 12 to 13 billion years, formed not long after the Big Bang. These ancient stars have very low metallicities, less than 1/100th the Sun's, indicating they formed from gas that had been enriched by only a few generations of stars. These old, metal-poor stars are fossils from the early universe, providing information about conditions in the early galaxy and the first generations of star formation. Studying these stars requires identifying them among the vast population of stars in Andromeda, which is challenging given the galaxy's distance. Spectroscopy of individual stars in Andromeda is difficult with current technology, requiring the largest telescopes and long exposure times, but it's possible for the brightest stars, particularly red giants. These observations reveal the chemical compositions of stars and allow astronomers to identify metal-poor stars that are likely very old. The distribution of old stars in the halo provides clues about how the halo formed. Did it form from stars born in the galaxy's protogalactic cloud, or from stars captured during mergers with smaller galaxies? The answer is likely a combination of both processes, with contributions from both in situ star formation and accretion. Andromeda's future is tied to the Milky Ways. The collision and merger of the two galaxies will be the defining event in the local group's future. The merger will transform both galaxies, erasing their spiral structures and creating a single elliptical galaxy. The process will unfold over billions of years, with multiple passages and increasing disruption until the galaxies finally coalesce. The merger will also affect the smaller members of the local group. Triangulum may collide with one of the galaxies or be ejected from the system. Dwarf satellites will be scattered or consumed. The entire local group will eventually merge into a single, large galaxy, the final product of billions of years of gravitational interactions. This fate is not unique to the local group. Mergers are a common part of galaxy evolution, and many of the galaxies we see today are the products of past mergers. Elliptical galaxies, in particular, are thought to form primarily through major mergers of spiral galaxies. The Milky Way-Andromeda merger will be a textbook example of this process, allowing astronomers to study galaxy mergers in detail. though unfortunately, no human observers will be around to witness it. The merger is far in the future, about 4 billion years from now, long after humanity is likely extinct or transcended in ways we can't imagine. But the physical processes are predictable, and simulations provide detailed predictions of how the merger will unfold. Andromeda is the farthest object easily visible to the naked eye. At 2.5 million light-years, it's by far the most distant object the average person can see without optical aid. The next most distant naked-eye object is the Triangulum Galaxy at about 3 million light-years, but it's much fainter and harder to spot. Everything else visible to the naked eye, stars, planets, nebulae, star clusters, is within the Milky Way, typically within a few thousand light-years. The fact that Andromeda is visible at all is a testament to its size and luminosity. The galaxy contains 1 trillion stars, and their combined light reaches us despite the enormous distance. When you look at Andromeda, the light entering your eye left the galaxy 2.5 million years ago, when early human ancestors were just beginning to walk upright in Africa. The photons have traveled across intergalactic space for millions of years, crossing the vast emptiness between galaxies to reach your retina. You're seeing Andromeda as it was in the distant past, a glimpse of history preserved in light. This is true for all astronomical observations. We see the universe not as it is now, but as it was when the light left. The sun we see in the sky is 8 minutes in the past. The nearest star is over 4 years in the past. The Andromeda Galaxy is 2.5 million years in the past. And when we observe distant galaxies with telescopes, we're looking billions of years into the past, seeing the universe as it was when it was young. Astronomy is a form of time travel, allowing us to study cosmic history. Andromeda is used to test galaxy formation theories. As one of the nearest large galaxies, Andromeda is a crucial target for testing models of how galaxies form and evolve. Its proximity allows detailed observations that are impossible for more distant galaxies. We can resolve individual stars, study stellar populations, map gas and dust, measure kinematics, and detect faint structures like tidal streams and satellite galaxies. These observations provide stringent tests for simulations and models. For example, models of hierarchical galaxy formation, which are based on the growth of structure in a universe dominated by dark matter, predict that large galaxies should be surrounded by hundreds of small satellite galaxies. Observations of Andromeda and the Milky Way initially found far fewer satellites than predicted, creating what's called the missing satellites problem. More sensitive surveys have discovered additional faint satellites, reducing the discrepancy, but questions remain about whether observations can fully account for all the satellites predicted by simulations. Other aspects of galaxy formation tested with Andromeda include the formation of disks and bulges, the regulation of star formation by feedback processes, the role of mergers in shaping galactic structure, and the distribution of dark matter. Andromeda's well-studied structure and properties provide a benchmark against which simulations can be compared, helping to refine models and improve our understanding of galaxy evolution. Andromeda's name comes from Greek mythology. In the myth, Andromeda was the daughter of Cassiopeia and Cepheus, the queen and king of Ethiopia. Cassiopeia boasted that she and her daughter were more beautiful than the Nereids, sea nymphs who served Poseidon. Angered by this hubris, Poseidon sent a sea monster, Cetus, to ravage the kingdom. An oracle declared that the only way to appease the god was to sacrifice Andromeda to the monster. She was chained to a rock by the sea, awaiting her fate when the hero Perseus, returning from his quest to slay Medusa, flew by and saw her. He fell in love with Andromeda and agreed to save her in exchange for her hand in marriage. Perseus defeated the sea monster, freed Andromeda, and married her. After her death, Andromeda was placed among the stars as a constellation, along with her parents, Perseus, and the sea monster, immortalizing the story in the night sky. The constellation Andromeda is located between Cassiopeia and Pegasus, and it contains the Andromeda Galaxy, which is often called the Andromeda Nebula in older texts. The constellation has been recognized since ancient times, documented by the Greek astronomer Ptolemy in the 2nd century AD in his catalogue, the Almagest. The galaxy within the constellation inherited the name, becoming the Andromeda Galaxy, though it has no physical connection to the mythological figure. Andromeda has been photographed extensively. It's one of the most photographed deep sky objects, a favorite target for amateur and professional astronomers alike. Its size, brightness, and structure make it an ideal subject for astrophotography. Amateur astronomers with modest equipment can capture images showing the galaxy's core and spiral arms. More advanced astrophotographers, using larger telescopes and long exposures, can reveal faint details like dust lanes, star-forming regions, and even some globular clusters. Professional observatories have produced stunning images of Andromeda at various wavelengths, from radio to gamma rays. The Hubble Space Telescope has captured high-resolution images, resolving individual stars in parts of the galaxy. One particularly famous Hubble image, released in 2015, is a mosaic of 411 Hubble images stitched together, showing a section of Andromeda's disk containing over 100 million stars. The image covers a region 40,000 by 16,000 light-years, revealing the galaxy's structure in unprecedented detail. The full-resolution image contains 1.5 billion pixels and can be zoomed in to see individual stars. It's one of the largest astronomical images ever produced and provides a remarkable view of another galaxy. These images are not just beautiful, they're scientifically valuable, allowing astronomers to study stellar populations, star formation, the structure of the disk, and many other aspects of the galaxy. They also serve an educational and outreach role, inspiring people to learn about astronomy and the universe. Andromeda is receding from us in 10 billion years. Wait, that seems contradictory. Didn't we say Andromeda is approaching? Yes, it is now. But on very long timescales, after the local group merges into a single galaxy, that merged galaxy will continue to be part of Laniakea and will continue moving within the local flow of galaxies. However, the expansion of the universe is accelerating, driven by dark energy, a mysterious component that makes up about 68% of the universe's total energy density. Dark energy causes the expansion to speed up, and over billions of years, this acceleration will overcome the gravitational attraction between increasingly distant structures. Eventually, even galaxy clusters and superclusters will be torn apart by the expansion. The merged Milky Way Andromeda Galaxy will remain bound. Gravity within the merged galaxy is strong enough to resist expansion, but more distant structures will recede faster and faster. In tens of billions of years, galaxies outside our local merged structure will recede beyond the cosmic horizon, the distance at which objects recede faster than the speed of light due to the expansion of space. At that point, they'll be forever unreachable, and the light from them will never reach us. The universe will become lonelier, with only the merged galaxy and perhaps a few nearby remnants of the local group visible. This distant future is speculative, and depends on the nature of dark energy, which is not well understood. But current evidence suggests the universe's expansion will continue accelerating, leading to a future where galaxies are isolated islands in an ever-expanding void. We've covered a lot of distance tonight, from the structure of Andromeda's disk to the ancient stars in its halo, from its supermassive black hole to its hundreds of globular clusters, from the spiral arms where stars are born to the tidal streams where satellites are torn apart, from its motion through space to the collision that will reshape the local group billions of years from now. But here's the thing, Andromeda is not separate from you. It's part of the same universe, governed by the same physical laws, made of the same matter. The light from Andromeda that reaches your eye left the galaxy 2.5 million years ago, but the photons that make up that light are traveling through the same vacuum of space that exists between atoms in your body. The atoms in Andromeda were created in stars, just like the atoms in you. When those stars died, they scattered their elements into space, and some of those atoms became part of new stars in Andromeda, while others became part of the gas cloud that eventually formed our Sun, Earth, and you. Andromeda and the Milky Way are approaching each other, drawn by gravity across millions of light-years of space. This same force, gravity, holds you to Earth's surface, keeps the Moon orbiting Earth, and binds the solar system together. It's a universal force, acting between all masses, from the smallest particles to the largest galaxies. The collision billions of years from now is inevitable, written into the fabric of space-time by the masses and motions of two galaxies that have been approaching each other for billions of years already. You won't see the collision, no human will, but in a sense, you're already part of it. The atoms in your body are part of the Milky Way, the galaxy that's currently moving toward Andromeda at 110 kilometers per second. You're a passenger on this vast cosmic journey, a temporary arrangement of stardust that happens to be conscious, aware, capable of understanding that Andromeda exists and that it's coming toward us. You're part of the universe studying itself, the Milky Way looking across 2.5 million light-years of space at its nearest large neighbor, the galaxy it will one day merge with. Andromeda reminds us that the universe is vast but connected. Distances that seem incomprehensible, 5 million light-years, can be crossed by light, by gravity, and eventually by the galaxies themselves. The cosmos is not static but dynamic, with structures moving, evolving, colliding, and merging over timescales that dwarf human history, but are measurable, predictable, understandable through science. The same atoms that make Andromeda's stars also make you. The same gravity that binds Andromeda's trillion stars also keeps you on Earth's surface. The same laws of physics that govern the galaxy's rotation also govern the chemistry in your cells. You're not separate from Andromeda, you're part of the same cosmic story, a brief chapter in the long history of matter and energy in an evolving universe. If you're still awake, there are more videos waiting. But if sleep found you somewhere along the way, then this worked exactly as it should. Rest well, knowing you're part of a universe vast enough to contain a galaxy of 1 trillion stars, a galaxy approaching across the void, a future merger that will reshape our cosmic neighborhood. You're connected to it all, through the atoms that make you, through the light that reaches your eyes, through the gravity that binds everything together. See you next time.